Hello and welcome to the second lecture of week 11 of the course Introduction to Generativity. This lecture, just like the previous lecture, will be close to 1 hour duration and will be split up into two parts or two lectures on the NPTEL website, namely lecture 61 and 62. Now, in the previous lecture this week, we focused on investigating the Schwarzschildgeometry, which is the gravitational field of space-time metric created by a spherical massive body, using Timelike geodesics. These Timelike geodesics describe motion of objects such as planets and comets around a spherical star in generativity, and we contrasted the trajectories with those resulting from Newtonian gravitation, namely Keplerian orbits. In particular, we found out that generativistic effects led to interesting physical phenomena such as perihelion precession of planets in the solar system. This has already been observed for Mercury almost half a century before Einstein had proposed VR and was waiting for an explanation, which VR provided. So in this lecture, we continue to investigate the Schwarzschild geometry, but this time probing it with light-like geodesics, which correspond to motion of light rays or massless point particles in general, such as the graviton in the gravitational field of a massive spherical object, for example, a star. This will lead us to interesting physical consequences as well. In fact, there will be optical phenomena in the context of VR, namely gravitational deflection or bending of light rays, and the gravitational retardation or time delay. As for references for this lecture, I will cite the following two sources. The first is Weinberg's textbook, Gravitational Cosmology, Chapter 8, Section 5. These pages, and section 7 of the same chapter, following pages. The second is Ohanian and Lufini's textbook, Gravitation of Spacetime. I'm using edition 3, chapter 4, and the relevant sections are 4.3 and 4.4. These are the relevant pages. Apart from these, as per usual practice, lecture notes will be posted on the NPTEL-NOC website. Let's look at the agenda today. First item on the agenda is to explore light-like geodesics in the Schwarzschild geometry. We will introduce general setup, general equation, and second item is to look at an interesting consequence, which is gravitational deflection or bending of light. And finally, the third item on the agenda is the gravitational time delay or gravitational retardation of light. So without further ado, let me begin the lecture proper with the first item on the agenda, which is examining light-like geodesics in the Schwarzschild geometry. Okay, let me remind you why we're studying this, because we're interested in the motion of trajectory of light in a gravitational field, in particular under the gravitational force of a spherical massive object. For example, our sun. First, we write down the geodesic equation. Where this is the affinely parameterized geodesic equation because the right-hand side vanishes. However, unlike the Timelike geodesic, this lambda, the parameter or the affine parameter, cannot be identified as the proper time. So we will just call it to be an affine parameter. Okay, we cannot identify it with the proper time because for light, the concept of proper time doesn't make sense. So this is a general geodesic equation in the general affine parameter. What signifies this will be light-like is if any 2 points on the geodesic, for any 2 points on the geodesic which are infinitesimally separated, that is separated by x, and x plus dx, the length square of the displacement vector should be light-like. In other words, ds squared should be, which is given by this, should vanish. Only then the solution of this will be correspond to a light-like geodesic. Okay, so we will solve this equation. Sorry about that. We will solve this equation subject to the light-like constraint. Now, light-like constraint, we have, this is the light-like constraint, as I said, if I divide both sides by d lambda, where then I get the velocity constraint, or in this case it's more accurate to call it the dispersion relation, because just like e squared minus p squared equals m squared is the dispersion relation, this is actually a relation analogous to that, except x dots are now, with the four velocities, they're given by this d smooth d lambda, where lambda is the prime parameter along the geodesics. So we have to solve this equation subject to this constraint. Alright, so let me remind you what the Schwarzschild metric is. So I'm using c equals 1 unit to reduce clutter of notation, otherwise we would have factors of c squared hanging around here and there. So just to make the notation a bit cleaner, let me use c equals 1 for the moment. In that case, the Schwarzschild metric can be written in this form which I've expressed in blue fonts. As you can see, e to the AR and e to the DR, these are given by this formula. So e raised to the little d, e raised to the minus little d is 1 minus 2 times m over r. Okay? And d omega 2 squared is nothing but the metric on the 2 sphere. This. And as you know, these coordinates are called the Schwarzschild coordinates. So I'm going to use Schwarzschild coordinates throughout. So the theta component of the geodesic equation leads to the same result as for the Timelike case. There is no distinction. As I said, the geodesic equation won't look any different, so the theta equation will not look any different for Lightlike geodesics. So which implies that the motion of the light rays will be confined to a plane, which we will call the equatorial plane, or which we will set to be the equatorial plane. Alright, so theta equation is solved for all values of the geodesic affine parameter, which is that theta is pi by 2, a constant. Next, we recall that the Schwarzschild metric admits two filling vectors. One is big C, which is one component 1 times the basis element del T, or if you write the components, it is 1, 0, 0, 0, and F, big F, which is again component 1, and basis is del phi. So if you write in terms of components, it is 0, 0, 0, 1. Alright? This is nothing to do with Lightlike geodesics per se, because this is general property of the Schwarzschild metric. Now, as you might remember, that existence of killing vectors leads to conserved charges along the geodesic. For the F, killing vector F, which is equal to del phi, the killing vector and the conserved charge I'm going to call little L. And as you know, it is given by this dxw lambda contracted with F. And since we are in the equatorial plane, its value works out to be r squared times pi dot. Similarly, for the path corresponding to the killing vector T, which is nothing but del T, we have to charge the temporal sign. And as it is conventional in the case of Timelike killing vectors, we define the charge with an extra minus sign, such that the final result in the expression is positive. So this is the conserved charge corresponding to the killing vector big C. Okay. Now, unlike in the case of Timelike geodesics, these two charges cannot be identified with angular momentum per unit mass and energy per unit mass, because if you recall, Lightlike geodesics correspond to notion of massless particles. So energy per unit mass is not a well-defined quantity, neither is angular momentum per unit mass. In fact, these quantities will change the moment we change lambda. Remember, lambda is an arbitrary affine parameter. So in some sense, these epsilon and L are completely dependent on parameterization. Right? Now, in the case of Timelike geodesics, there was a special parameterization which is called the Timelike proper time parameterization, in which these have some physical meaning. However, for Lightlike case, we see that there is no preferred parameter, so this is completely ambiguous. And in fact, what we will do is we will rescale the affine parameter such that one of the charges will become 1. Okay, particular the time will be removed from our expression because it will scale to 1. Alright, so if I rescale my affine parameter lambda to lambda by prime, I see my job is done because so my new affine parameter lambda prime is epsilon lambda by prime. Let me think about it. I think it's epsilon. Alright, so lambda can be written as then epsilon prime over epsilon. So lambda prime over epsilon. And then if I substitute this in this equation, we will see that this epsilon will cancel from both sides and give you 1. Alright? And similarly, you might be worrying that, okay, I removed the sign from this equation because the left hand side and right hand side both have the same power of the sign and they cancel out. However, if I rescale, if I replace lambda by lambda prime by epsilon in this equation, I might get an extraneous factor of epsilon. Well, that can be mitigated if I rescale L as well. Okay, if I redefine L as well. Define instead of L, I define L prime, which is L over prime. And then we can see from both sides again epsilon will disappear from this equation. As a result, we can write that phi dot L over R square, and T dot is e to the minus AR, because epsilon is just 1 now after performing this rescale. Okay, so because lambda is a completely arbitrary affine parameter for the case of Lightlike geodesics, we can do this without any loss of generality. And now we have only one conserved charge, L, hanging around in the expressions. Okay, so before I go to the next slide, I would like to remind you that these equations are first order ordinary differential equation and can be readily integrated provided we know R as a function of lambda. Okay, if R as a function is known, as the lambda is known, these equations can be solved to give you phi as a function of lambda, and the second equation can be integrated to give you T as a function of lambda. That would in principle determine the trajectory of the geodesic. Remember, theta has already been fixed to pi by 2 for all times, for all lambda. So it's already determined in some sense. But basically the idea is the only thing we need to solve is the radial coordinate. Once we know the radial coordinate, these two equations will solve us, give us phi and t, and then we'll be done. So let's look at the radial equation. In particular, we will first look for the orbit. Remember, the orbit is given by r as a function of phi. Okay, the shape of the orbit. So let's look at the orbit. And in general, if you try to work with the r component of the geodesic equation, it is a complicated second order nonlinear ODE, and it's hard to solve. So we will use the same trick we use for the Timelike geodesics, which is to solve the Lightlike geodesic system. Okay, so which is this equation, given a x dot nu equals 0. When you write explicitly, plugging in the question metric, you get this condition. So this is first order. The first order equations are solvable in many cases. So again, phi dot, I'll be writing it in terms of L over R square. T dot, I will write T minus AR. And then if I divide both sides by phi dot square, I will get the orbit condition. So this is what I get. The ratio of dr d lambda to dt d lambda, d phi d lambda has been set to dr d phi because I'm interested in finding out the orbit. Okay. We will later on work out how the function of lambda over t as well. for the time being, let me just focus on the orbit. So I'm trying to solve for r as a function of phi. Alright. So this is the equation we need to solve. This can be massaged into a first order equation, and one can write down a closed form solution, which is this. Alright. So you might be wondering what this plus and minus sign is about. It will turn out that phi is actually a double valued function of r. Let me just make a diagram to make this obvious. Let's say we are in the gravitational field of a spherical star like the sun, and let's say a light ray which is coming from infinity. Now, had the gravitational force of sun not been there, it would have continued on its merry way, straight in a straight line. But because of the sun, we will see that the orbit light will get attracted towards the sun and then turn it on like this. So, for a given value of r, radial separation, we can see there are two solutions, which have the same value of r. Okay, so this plus and minus will correspond to the upper arm and upper limb and the lower limb. Okay, and the incoming part and the outgoing part. So phi is a double value function, and something like that. Okay, so we write down a closed form solution. Now let's consider the point r equals to r0. Let me refer to this diagram here. So this point, this distance is r0. This is the point of closest approach, or what we call the periapsis. So r0 will be the periapsis of the point of nearest approach. At the point of nearest approach, because r is the minimum, dr d phi will be 0. And if we plug this in the Lightlike constraint, what we get if we, this term will be 0, and what we will get is r, L in terms of values of things at r0. Okay. L as a function of r0. Alright, so L is determined in terms of the value of the radial coordinate and the periapsis. Okay. In case of the sun, this would be perihelion. In case of Earth, it would be perigee. Now, I've rewritten the solution in terms of R0, eliminating L. So if I eliminate L in favor of R0, this is what I get compared to the last formula where there was L squared. Now I have something else. We have some factors of R0 squared, and e raised to the little a of R0. Alright, so consider light approaching from infinity to some point R, radial location R. Now that angle, if I take the absolute value of the angle, or the change in the limit angle, will be given by this formula. Okay, so let me refer to the diagram again. So this is R, and this is the value of the limit angle phi of R. And then phi of infinity will be somewhere phi. Okay, so the difference between the limit angles is given by, in fact, the magnitude, because for upper and lower you have to distinguish the two different signs. So instead of that, for convenience, we'll represent with the absolute value, which takes out this plus minus ambiguity entirely, and we describe the increasing solution. So this is increasing, so this will be integral is going to be positive, and the answer this is equal to the change in the limit analysis. Alright? So this is although this is a closed form solution, it is not that helpful because we don't get an idea of what this function is until we perform the integral. And performing the integral is in general very hard. So we will take an approximate approach or perturbative approach, reminding ourselves that the gravitational field is actually quite weak. Okay, so the light is moving under a weak gravitational potential. So gravitational potential phi, which is the latest quantity, divided by c squared, this dimensionless ratio is versus 9 to 1. This is what we are going to prove with gravitational field. And then e raised to the r and e raised to the b, which can be written at this point. And you can see this is nothing but twice phi over c squared. I will consider this quantity to be much smaller than 1 and then expand in powers of this point. Okay? So expand in powers of g and m r over c squared and g and m r0 over c squared in both cases. And after expanding the integral in powers, we will then integrate term by term. So this will be a perturbative solution. So this is expansion, and showing the expansion. And I'll leave it as a homework to perform the integral into first two terms. First is order 0 in g and m, and the second term is linear order in g and m. So if you work this out and if you look at the homework exercise, if you do that, you can find that the change in the limit angle is given by this inverse, which will be there no matter whether, even if the mass was zero. Even if there was the light ray was going undeviated in straight line path, and the second term would represent some kind of deviation. Now, at the nearest point of the nearest approach, when r is equal to r0, we can substitute r equals r0 in the right hand side, and approximation that is Newton times square, which I'm not bothered to write down, but you can write down. Leading order correction is already pretty small, and this is sin inverse of 1 is pi by 2, and these two terms can vanish, and then we need to just look at twice of this guy. So this is what we have. Okay, so this is the change in the limit angle from infinity to the point of nearest approach. Let me draw the diagram once again. So here we have something like the object. And arriving light is tending towards the sun, and then leave something like this. So then the way I have drawn it, the limit angle at the nearest point of nearest approach of the axis and 0, this angle is actually pi from the x-axis. And at infinity you can take some other value. We have drawn it quite as 0 is nothing but pi. Okay, but the major axis need not be the x-axis, and then in that case this is the formula. Right, and while moving away, there'll be an equal amount of deflection, gain in the angle, so that twice of this will be given by twice of this side, right? Which is this, very obvious. Now, in the absence of a central body, when m is 0, no deflection would be when this angle twice of this is exactly equal. Okay, and this angle is exactly equal to pi. On the other hand, when the mass of body is non-zero mass, has non-zero mass, then the deflection angle delta phi is actually, I don't want to define it as delta phi, with delta. Just imagine this is delta phi. This angle delta is this minus pi, which is this quantity in the last slide. So this minus pi will be this. Okay. So you might be feeling a bit unclear about what is the deflection angle. So the deflection angle is nothing but the angle between reflectance. Let me draw the diagram once again. So we have a simple massive object, and then light ray is coming, and it gets turned around this time, something like this. So the deflection would be at infinity, that is, when we draw a tangent from infinity, which would, if the light had not gone on undeflected, then it would have gone on this dotted line, but instead it gets deflected pulled around, and at infinity, let me draw the tangent at infinity here. Draw this somewhere here. So this would have been the original trajectory, original direction of motion. Now it has been turned around to this. So this angle is delta, the deflection, the deviation from the original to the actual. Okay, so it is going in this direction. Now, this angle delta is nothing but phi minus this angle, and we call it the double. So, and this angle is twice of this delta, right? Remember, the trajectory is symmetric around the x-axis, so these three angles are there. So delta is actually pi minus twice of little delta. Right? This full angle is pi, and then delta, big delta plus twice of little delta is pi. So we have this relation, and this, let me draw the radial point at infinity, something like this, and this would be infinity, and of course we have this angle pi, which is nothing but pi r0. We have set it up our coordinate system. Pi at r0 is always pi, but this formula is written for general case. Let me take it to pi, and the difference between these two azimuthal angles is nothing but this and this, and delta have a relation because this will delta this angle, and we call it beta. So the difference between the azimuthal angles plus delta plus beta is also pi. Changing the azimuthal angle with beta is also pi. And remember, when you're at infinity, this angle beta is vanishing because there's no difference between the position vector and the tangent. They almost the angle gets squeezed as you go. This beta angle gets squeezed as you go further and further away. And in fact, in the limiting case, when you go all the way to infinity, beta is actually 0. So then delta is nothing but pi minus pi. And if you plug this here, you should get the reflection, okay, in terms of delta minus pi. Okay, this formula you should be able to get. I'm sorry, and then this one we already put in the last slide. All right. So a little bit of Euclidean geometry, and you should be able to see that the deflection of the last angle, deflection angle delta, which is the angle between the original intended direction and the actual direction due to gravitational pull of the planet or pull of the star, is delta, which is given by this quantity, which we had worked out the leading order to be 4 g m divided by r0 and c squared. So brought back formula, c squared is the formula because we want to plug in some numbers and show what is the value in particular physical cases. So in particular, we see this deflection angle, which is actually very small, because the gravitational field is very weak. So this angle is very small, as you can see, of the order of a few odd seconds. This angle will be maximized, again, don't think about this delta, is maximized when r0 is minimum. The smallest value of r0 possible would be, or the distance of nearest approach to be equal to the radius of the massive object at the center, okay? Because then the light ray would be at grazing incidence, like this, something like that, almost grazing the surface of the star. So the minimum possible value is r star. In this case, I put r sun. And the mass also, you can put the solar mass, and you can work out what this magnitude of this deflection would be. Again, fine, this delta. And it turns out the answer is of the order of 2 arcsecond. And computing this is left as a homework exercise. I think it might be of the order of 1.75 into exactly 2, but this is around 2 arcseconds. And in fact, it is twice the value which is predicted by Newton's theory. Now, in Newton's theory, you can think of light as a massive particle with mass and gamma equal to h nu over c squared. You can pretend that light is a classical particle of relativistic mass which is given by this. Non-relativistic mass which is given by this. And then you can apply Rutherford's formula to find out what is the deflection angle, or what is the angle of deflection. And in fact, the Newtonian expression, which is given by the famous Rutherford formula, only leads to half the amount of deflection which we observe. Okay, so as I said, this has been observed. Actually, it was observed in 1919 by Alfred Eddington during a total solar eclipse. Now, the idea was that during the total solar eclipse, the sun gets completely blacked out during the eclipse. Let me make this opaque. So this is the disk of sun, which becomes opaque during the eclipse. And then there are stars behind the sun. So let's say this is Earth, E, and there were stars in the background, which could not be visible to us because they lie in the shadow region. Remember, the sun has been blocked out, and these stars are behind the sun, so they're in the shadow region. But because of the gravitational deflection of light, these stars became visible because light was pulled around the sun, and as a result, one could see images of the stars. If you refer to the images of the star, okay, one could see that. So, observed position of stars in the background was different from their true position or expected position. People knew these stars were these are stars that had been studied in astronomy for a while, and people knew what they were supposed to be. And instead of what they were supposed to be, there appeared to be multiple images of the same star during the eclipse when the sun is not in the field of view. Their position during the eclipse is different from what their expected position was, which was known because they've been observing these stars for a while. And so this effect was observed during the eclipse. And in fact, I think there were some measurements also which came close to this value, but these measurements are highly debated. And I think even future experiments have not been, the experimental errors have not been eliminated to a great extent to trust them very well. But still, it gives an experimental confirmation of general relativity. And this was in fact the first experimental confirmation of general relativity. And it catapulted Einstein and general relativity to instant stardom and instant success. So that this is as an experiment, it is very difficult to perform, and also the errors are pretty large. Especially, you need to work with the optical telescope, and this is not an easy experiment to do. So in general, the fact that massive objects would deflect light around it like this and produce different kind of optics, different kind of effect, is known as gravitational lensing effect. Again, it is used in astronomy and astrophysics very much. So, now, one can nowadays, I think this experiment can be performed with radio waves instead of optical waves. So we don't need to wait for an eclipse. The reason we need to wait for an eclipse is that otherwise things which are behind the sun will not be visible anyway because the sun is too bright, and we need the eclipse to block out the sun, block out the disk of the sun. that if we do this experiment with radio waves, then we don't need to block out the sun at all, because radio waves we don't really see using optical telescope. We use radio telescope. So then we just need astronomical source or source of radio waves. We have many such. We know many such sources. Many stars radiate radio waves or emanate radio waves, and we just need to wait for a moment when the sun is blocking, or the technical term is occulting, when the radio source is being occulted by the sun, and then we can look at the radio waves coming from the direction and figure out its observed location versus its actual location. Okay? So it gets a bit easier, and you don't have to wait around for eclipse if you're working with radio sources instead of optical sources. But still, the experimental errors in this setup is extremely large, and it's always not the best, most refined way to verify general relativity. Still, as I said, this is the first classic test of general relativity, and it catapulted Einstein to instant stardom.